Let's do some examples. A term is given by tk is equal to a 3 upon 2 to the power of k minus 1 plus bk, where a and b are elements of real numbers. If the first term is given by 3 and the third term is given by 6, solve for the constants a and b and write down the kth term of this particular sequence. Using our first criteria, where the first term is 3, using our second criteria, where the third term is equal to 6, now we got two equations with two unknowns, a and b being the unknowns. Let's write a matrix with all the coefficients in there. In our first equation, we have the coefficient of a is 1, the coefficient of b is 1, and all of that is equal to 3. In our second equation, our coefficient of a is 1, our coefficient of b is 12, all of that equals to 24. Row reducing this, what we have here is that a is 1a, or a, is equal to 4, and b is equal to minus 1. Therefore, our term of this particular series is given by the kth term of an arithmetic progression is given by, so the kth term is given by 3k minus 1 over 6. Without assuming the formula for the sum of an arithmetic progression, prove that the sum to n terms is equal to n on 12 times 3n plus 1. Well, because this is an arithmetic series, for us to get the sum of n terms, we're going to write the series forwards and backwards and sum vertically. Let's write it for k. Let's write for k equal to 1, k equal to 2, k equal to 3, and so on. And so on. Let's write it for n minus 2. So our first three terms are 1/3, 5 over 6, 4 and 3. Our last three terms are 3n minus 7 over 6, 3n minus 4 over 6, 3n minus 6 over 6. Let's write the series forwards first. Let's now write the series backwards. Let's add them vertically. What we have now is, well, 1/3 plus 3n minus 1 over 6 is going to be 3n plus 1 over 6. 5, 6 plus all of this, 3n minus 1 over 6 is going to be 3n plus 1. But how many 3n plus 1 over 6's do we have? We have n of them. So 2. Let's bring the 6 outside, and let's bring this 2 to the right hand side. The second and seventh terms of an arithmetic progression are -5 and 10 respectively. Find the fifth term and find the least number of terms which must be taken for the sum to exceed 200. Well, from our first criteria, where the second term is -5, the second term of an arithmetic series has one common difference added to it. The seventh term of an arithmetic series has 6 common differences added to it. From equation 1, we see that let's simply take this a equal to -5 minus d and substitute it into equation 2. If the common difference value is equal to 3, then the first term value is given by -5 minus 3. For the least number of terms for the sum to exceed 200, we know that a sum of an arithmetic series is going to be but we want the sum to exceed 200. Now this is a quadratic in terms of n. Let's just put it in a quadratic formula. We have two potential values of n being greater than -8.8060 or n greater than 15.14. Well, we disqualify this solution because the number of terms can never be negative. So we accept this solution, but the number of terms can only be a positive integer. So because n is greater than 15, the first positive integer greater than 15.14 is n equal to 16. A piece of string of length 5 meters is cut into n pieces in such a way that the lengths of the pieces are in arithmetic progression. If the length of the longest piece is 1 meter and the length of the shortest piece is 25 cm or 0.25 meters, calculate n, the number of pieces. Well, the very last term is given by but what is a, the very first term? And all of this is equal to 0.25 meters. Or if you prefer, but we know that the entire piece of string, or the sum of all the n parts, is going to be 5 meters. But what is n minus 1 times d? That's minus 3/4. The total number of strings is just equal to 8. A person pays a premium of $30 per annum for 18 years. How much should the person receive as a lump sum after paying the 18th premium, assuming compound interest at 5% per annum? Well, initially, the amount paid at the second year at 5% interest is at the third year at the 18th year. Hence, the total amount is given by from a sufficiently long piece of string, 10 portions are cut off successively. Their lengths form a geometric progression. The first and second terms are 10 meters and 9.5 meters respectively. What is the total length cut off to the nearest meter? If the process is continued, as long as the portion cut is not less than 1/3 meters, how many portions are obtained? Well, firstly, the very first term is 10 meters, the second term is 9.5 meters. Hence, their common ratio is given by is there 10 portions will sum to 10 terms. The sum to 10 terms is 80 meters. As each piece of string is cut off is representative of a geometric series, the term of a geometric series is given by. We want each piece of string to be greater than 1/3 meters. Our number of pieces is going to be approximately 67.31. but because the number of terms can only be an integer, we accept the solution of k is equal to 67. The first three consecutive terms of a geometric series are x minus 5, x minus 1, and 2x plus 4. Explain why x minus 1 times x minus 1 is equal to x minus 5 times x minus 4. Also solve for x. Also find the value of the fourth term. Well, as this is a geometric progression, there must be some sort of a common ratio. Expanding all of this, we're going to obtain put it in a quadratic formula. We're going to get x is equal to minus 3 or x is equal to 7. For the fourth term is always given by t4 is equal to t1r cubed. We got x equal to minus 3 or x equal to 7. By common ratio. Ratio again. So this common ratio is equal to 3 and that common ratio also equal to 3. By common ratio, this is equal to half. By this common ratio, it's also equal to half. So we get two possible values of common ratios. Therefore, our first term is either equal to minus 8 or 2. Minus 3, minus 5. To check, let's use the values of t1 and let's use two possible values of t1 equal to minus 8 and t1 equal to 2, and let's put them together with the common ratio values of r equal to 3 and r equal to half. Put it on this table. So these are all the common ratio values of half. Here are the common ratio values of 3. Here are the values of 3 or minus 3, and here are the values of 7. And we see that all of this form a geometric progression. An arithmetic series and geometric series have r as the common difference and common ratio respectively. The first term of an arithmetic series is 1 and the first term of a geometric series is 2. If the fourth term of an arithmetic series is equal to the sum of the third and fourth terms of the geometric series, find three possible values of r. Once again, an arithmetic series and a geometric series have r as the common difference and r as the common ratio respectively. The first term of an arithmetic series is 1 and the first term of a geometric series is 2. If the fourth term of an arithmetic series is equal to the sum of the third and fourth term of the geometric series, find the possible values of r. Well, we know that an arithmetic series is given by the first term plus the fourth term, plus three common differences. In this case, the common difference is written as r. Is equal to the sum of the third and fourth term of a geometric series. In this case, it's going to be 2r squared plus 2r cubed. We get this cubic equation. So this cubic can be decomposed into a linear function times a quadratic function. These two factors, a linear factor and a quadratic factor. For the quadratic factor, let's further factorize it. We got three values of r equal to 1 or r equal to minus 2 plus or minus root 2 all over 2. When the magnitude of r is less than 1, find in the form p plus q root 2. Part A, the sum to infinity of the geometric series. B, the sum of the first 10 terms of the arithmetic series. We're told that the magnitude of r is less than 1 because this is an infinite geometric series, so the magnitude of the common ratio must be less than 1. With that said, we can disqualify r is equal to 1 and we can disqualify r is equal to minus 2 minus root 2 on 2, leaving us with just with that common ratio value, our sum to infinity is 8 on 7 plus 2 on 7 times root 2. For part B, for the sum of the arithmetic series, the sum of the arithmetic series is given by n over 2 times 2a plus n minus 1d, where n itself is 10, a is 1, and the common difference is minus 2 plus root 2 all over 2. Our sum to 10 terms is given by minus 35 plus 45 on 2 root 2. It is given that a, b, c are the first three terms of a geometric progression, and it is also given that a, c, b are the first three terms of an arithmetic progression. Part A, show that b squared equal to ac and that c is equal to a plus b on 2. Part B, show that 2b on a all squared minus b on a minus 1 is equal to 0. Part C. Find S infinity of the geometric progression in terms of a. Well, because we know that a, b, c are in geometric progression, there must be some sort of a common ratio happening. Because we know that a, c, b are in arithmetic progression, there must be some sort of a common difference happening. Putting the expression of the common difference into the expression of the common ratio. Let's divide everything by a squared. Because we know 2b on a all squared minus b on a minus 1 is equal to 0, let's not hurt our eyes and let's just say is equal to capital X. What part B will become is, let's put this in the quadratic formula. We get capital X is equal to minus 1, is equal to 1, or capital X is equal to minus half. But please bear in mind that capital X was B upon A. With that said, if we're going to get some sort of an infinite geometric series, we need the common ratio to be between minus 1 and positive 1. So we reject this solution in favor of this one. This is our sum of infinite terms in terms of A. Obtain the kth term of the series 1 times 2 plus 2 times 5 plus 3 times 8 plus 4 times 11 plus 5 times 14 and so on, and prove that the sum of the first n terms is given by n squared times n minus 1. Well, we see that the kth term is written by k times 3k minus 1. And we know that the summation of n terms is given by summation k equal to 1. Let's put tk into here. But we know that the summation operator is distributive. And we know that the summation operator, we can pull out any constants. Now what are these two portions, these two partial sums? We have the summation of all the integers from 1 to n, all of the integers squared. It is given by Over here, we got this the summation of the first n number of integers. Combining these two fractions. The numbers a1, a2, and a3 are as follows. a1 equal to 2, n plus 1 is equal to 2 times a1 plus a2 plus a3 and so on all the way to an, where n is the element of all positive integers. By first finding a2, a3, and a4, prove that a2, a3, and a4 from a geometric progression. Then find the sum of the first n terms of this geometric progression. From this formula, a2 must be given by 2a1, which is given by hence a2, a3, and a4 are in geometric progression with common ratio equal to 3. For the sum of the first n terms, we're going to see that if we were to put a1 with a2, a3, a4, it does not form a geometric progression, but a2, a3, and a4 do form a geometric progression. So what we need is that we have a1 plus s, because all of these guys form a geometric progression except that guy. But the very first term was sum to n terms of the series ln a plus ln ab plus ln ab squared plus ln ab cubed and so on, and later on show that your solution is equivalent to n on 2 times ln a squared b to the power n minus 1. For this first guy, because we know that if we have a log of a product of things, is equivalent to writing the log of the sum of the logs. We also know that a log of a stuff with a power, we can bring the power forward. And let's also group all the ln a's together and all the ln b's together. Let's factor out the ln b's and bring the powers down. Incidentally, we have n number of ln a's. But our very first term had no b's. Hence, our very last term would have n minus 1 b's. This is b to the power of 0 actually. What do we have here? When we did the sum of 1 plus 2 plus 3 plus 4 plus all the way to n, we had, but now we have that same sum but shifted backwards by 1. So what we have is over here. For part B, it's just doing a whole bunch of log laws really. We know that if we have a coefficient in front of the log, we can bring the coefficient to become the power of the stuff inside the log. Now these are the sum of two logs, so we can put them as a product of the two stuff inside the logs. For a geometrical progression, S is the sum of the n terms, P is the product of the n terms, and R is the sum of the reciprocals of the n terms. Prove that S divided by R all to the power n is the same thing as P squared. For S, well, this is a geometric series, so the formula for a geometric series is, for R, because it's the sum of the reciprocals of a geometric series. Let's divide the both of them with each other. Raising S on R to the power of n. For P, let's factor all the A's. And how many A's are there? 1, 2, 3, 4, all the way to n number of P's. And all the R's, they themselves form R to the power 0, R to the power 1, R to the power 2, R to the power 3, and so on. So R to the power of squaring all of this.